Hey, we're back here. It's Monday. We're continuing on with our discussion of chapter 29. Okay, so back here. So today we're going to go over magnetic fields due to loops, coils, and solenoids. There's a lot of practical uses of these in motors and in magnetic resonance imaging and in many areas of technology that we're going to go over. So we're going to study the magnetic field due to a single current loop, a coil, which is several loops. We're going to digress for a second to show that a single current loop produces a magnetic field of a magnetic dipole. In other words, it produces the same magnetic field as the electric field produced by an electric dipole. And then we're going to go into a solenoid, which is a tightly wound coil, which is used for electromagnets and in MRIs. So required reading, we're going to be skipping section 2910. This chapter never ends. I mean, this is a long chapter anyway. So we're going to skip the last section. The homework I uploaded, I extended the due date a little bit. I made it due Saturday. Originally it was due Saturday night. I extended it to Sunday morning. Can't really make it any later than that because I have to post the solutions in time for Monday's exam, which covers chapters 27 and 29. So this is our last unit exam. So far to this point, what have we done in this chapter? Okay, we studied the magnetic fields of bar magnets, right? These stationary magnets with a north pole and a south pole. And we saw that if you sprinkle iron filings or if you place a compass at all of these points, they'll give the orientation of the magnetic field. And the magnetic field is very strong near these ends, which are the poles of the magnet, and it gets much weaker out on the sides, right? And the field lines go from north pole, they exit the magnet from the north pole of the magnet, and they re-enter back in the south pole, and then they're very strong inside the magnet. They form loops. And we discussed earlier in the chapter that you can sort of think of the North Pole as behaving like a positive charge, and you can think of the South Pole as behaving like a negative charge. And so if you stick a North Pole next to a North Pole, they'll repel. But if you put a North Pole of a magnet next to a South Pole of another one, they'll attract. Okay? So you should be able to sketch these magnetic fields due to a bar magnet. Then we discuss the point charge, so a moving proton or a moving electron, and the equation for the magnetic field of that was given by the Biot-Savart equation. So you can use that equation for calculating the magnetic field produced by a point charge. Now that itself was not a particularly useful equation, but its main use is that if you have a current or many charges moving, we can use the superposition of the magnetic fields due to the individual moving charges to get the fields due to more realistic charge distributions or current distributions. And so we studied after that the magnetic field of a current in a wire. Right? We saw that the magnetic field lines, if the current is moving this way, are given by loops. The magnetic field lines are loops surrounding the wire, and the field gets weaker. It goes as 1 over r, where r is the distance from the wire. And to get the field direction, we take our thumb and you point it in the direction of the current, and you curl your fingers, and that gives the direction of the magnetic field. So the right hand is curled, and you see that they're curling in this counterclockwise sense, and that gives the direction of these field lines. Okay, they're going counterclockwise. So we studied the field due to a current in a wire. Today we're going to get into loops of wire, first starting with a single loop and then getting into many loops, like what's called a solenoid. And so that's where we're going next. And then after that, we're going to, after showing that moving charges create magnetic fields, we're going to study the effects of these magnetic fields in return on moving charges, right? So just as electric fields can exert forces on charges moving in the fields, moving charges in magnetic fields will experience magnetic forces. So that's where we're going in the next lecture. So let's start with a current loop of wire here. So we want to get a good foundation for the field due to a single loop before we go on to several loops. Okay, so here's a loop and it has some radius r, and we want to calculate the field. Okay, in practice, if the loop is closed, how do you get a current through here, right? We need to connect something to it which circulates a current. So in reality, a practical current loop looks pretty close to the ideal one, but you have a little bit of a air area here where the current comes in and where the current comes out, and that allows it to circulate. So the author goes through in example 29.5. You can apply the Biot-Savart law. If you take each of these little infinitesimally small sections of the loop and you calculate the field due to each of these, and then you add them up using superposition, he goes through that to get the magnetic field of the whole loop. We're just going to use the results, but I want to show the geometry here. So the main use that we want to find here is we want to find what the magnetic field is along the axis of the loop. So here's the plane of the loop, and the axis is if you drew a line perpendicular to the loop, and we'll call that the z-axis, okay? And so we want to find the magnetic field at some point along the axis at some distance z from the loop center. And it's not so intuitive here, but if you go through this example, and I encourage you to do it, the author will show you that the contributions from segments that are across one another on the circle, their contributions along the x and y directions cancel in pairs. And so, in other words, there's no magnetic component along the x and the y direction, but the components along the z direction, which is along the axis, add. And he derives that the magnetic field at some distance z from the loop is along the z-axis, and it depends on the current and on the cube of the distance, so z squared cube. We'll get into that limiting case in a minute. And you're going to see in a little bit, this is an identical equation to the electric field produced by an electric dipole, which are positive and negative charge separated. We derived an identical equation for an electric dipole in chapter 23. So we'll see in a little bit that the magnetic field produced by a current loop is the field of a dipole, a magnetic dipole. Now, it's often interesting to note what the field is at the center, okay? And if we set z equals 0, because we're at the center of the loop, you can put 0 here, and you get that the magnetic field goes as I times r squared divided by r cubed, and r squared over r cubed gives r, where r is the radius of the coil, not the distance from the, well, it is the distance from the center to the end, but, and so that's the equation for the field at the center. So we're not going to derive these. I think it's too much of a digression. So I encourage you to look at that example and to be able to use these equations on the exam. So write them on your cheat sheets. Now, if we know what the field is due to a single coil, then the field due to n closely wound turns of wire, or if you have n coils, n loops, and they're all together, all of the fields add up in the center, and the field is n times stronger than the field due to a single coil. So if you go back here, it's mu naught times over 2 times I over R, and if you have n turns, the field at the center is just n times bigger than this. And similar to that, the field points along this axis. Now, this is interesting because what this says is that, well, one single loop that may not create a very strong magnetic field, if we wind n of these coils or n of these loops together as a coil, we can generate a very strong magnetic field in the center, and that's where we're going to get into solenoids. So a magnetic loop is what's called a magnetic dipole. And before we get into the direction of the loop, the direction of the field, which we'll get into in a minute, and how to determine that. So far, we only showed that it's equal to z along the axis. Let's discuss magnetic dipoles for a minute here. Back here. So my claim is that the magnetic field due to a current loop, which is right here, is the same as an electric dipole. Okay, and we'll see that in a minute. And so this produces the field of a magnetic dipole. Okay, so it's the exact same field as the electric field as far as shape as the electric field is for an electric dipole. So to do that, we need to define, so you can write the field. Here's our equation for the field along by a single loop on axis. And if we multiply and divide by pi, we note that pi r squared is the area of the loop. Okay? And we define this quantity called the magnetic dipole moment. It's a vector, just like the electric dipole moment. We define that as the product of the current through the loop multiplied by the area of the loop. If it's a circle, it's pi r squared. If it's a rectangle, it's just length times width. So we're going to define this dipole moment, the magnetic dipole moment, as the current times the area of the loop. Okay. And so this is going to play the same role in magnetism as the electric dipole moment P did with electrostatics. So to find the direction of the magnetic dipole moment, you take your right hand and you curl your fingers in the direction of the current. So in this case, you would take your hand and you would curl it counterclockwise, and your thumb points in the direction of the dipole moment, which is upward in the figure. Okay, so the dipole moment is a vector, just like the electric dipole moment is a vector, and its magnitude is equal to the current times the area of the loop. Okay, so now we can write the equation for the magnetic field of the loop. If you write I times pi r squared as I times A, and then I times A as this magnetic dipole moment mu, then we get that we can write that the dipole moment is in the magnetic field is in the same direction as the dipole moment, and it obeys the exact same equation as that for an electric dipole, where for the electric dipole you replace the magnetic dipole moment with the electric dipole moment, and you just have a little different constant here. We have epsilon naught. So this is the equation that we derived before for a loop, only now we have it written in terms of the magnetic dipole moment. Okay? Now it's unfortunate, but we're limited by 26 letters in the alphabet and the number of Greek letters. But you have this mu naught, which is a constant, the permeability of free space, and then your author used this mu, which is that Greek-looking U. That's the magnetic dipole moment. These are not the same thing. This is a vector, and it's the magnetic dipole moment, and this is a constant. Okay, so unfortunate, but it is what it is. So this is the equation on the axis for a magnetic dipole moment. Okay. Now we can again show that if you have Z is much, much greater than R, which is almost always the case. So in other words, if we're much further away from the loop than the radius of the loop, and these loops are usually small, this is usually pretty easy in practice. If Z is much, much further than R, we can neglect R squared here, and then you get the denominator as Z squared plus 0, which is Z squared to the 3/2, which is Z cubed. And this is the exact same equation, is the electric field for an electric dipole, except you replace electric dipole moment with magnetic dipole moment, and you have a different constant. Okay, so they produce the same field on the axis. Okay, now it's a little more complicated. You can do it in principle, but it's messy. You can calculate the magnetic field at any point, and we can draw the field, and you would see that the magnetic field looks exactly like the electric field due to an electric dipole. Okay. The field is along the axis, along the z-axis here, and then as you get away from the loop, the field lines are circles. Okay. And it's exactly the same magnetic field as a bar magnet. Okay. So this is why we call a current loop is often called an electromagnet. You run electricity through it, current, and it produces a magnetic field, and you can pick up paper clips and things like that. So let's get into, here's the direction of how to get the magnetic field. Okay, so in this case, if you look at the left figure, at the top of the loop, the current is coming out of the page toward you. At the bottom of the loop, you see the tail of the arrow, the current is going back into the page. And so the current is going like this. And what that means, if you curl your hands in the direction of the current, your thumb points in the direction of the magnetic field, the field lines emerging from the center of the loop. And so your thumb would point to the right, and that means that the magnetic field lines are coming out of the center toward the right. Okay. Now, the field lines, just like a bar magnet, they make the field lines are circles, and so they're going to circle back. They come out from the right end, they circle back, they come back into the loop from the left end. Okay? And if you look at the analogy with the bar magnet, the field lines come out of the North Pole, they make a loop, and they come back through the South Pole. And so the side of the loop in which the field lines are coming out from the center behaves exactly like the North Pole of a bar magnet, and the side in which the field lines are entering back through the loop behaves like the South Pole. So we will call this direction from which the lines emerge the North Pole of the magnet, and we call the other side the South Pole. Okay? And they behave exactly like a bar magnet. You can take a current loop here, and if we put this bar magnet and we brought it toward it, they would attract one another because South Poles and North Poles like each other. Here's another picture of the current loop. So let's get more practice at getting the direction here. So here the current is going counterclockwise. And so if you curl your hand in the direction of the current, your thumb is pointing out of the page, and so that gives the direction in which the magnetic field lines are emerging from the center. So thumb points out of the screen toward you, and so the magnetic field lines emerging from the center of the loop or inside are coming out of the screen toward you, and then outside the loop they're forming a circle, they're going back into the screen, and then they come back in. They're forming loops. And so in this case, the north pole of the magnet would be the side of the loop toward you, and the south pole of the magnet would be the side of the loop into the screen. So that's the way, if you know the current direction, that's the way for getting the direction of the magnetic field, okay? You curl your fingers in the direction of the current, and your thumb gives you the direction of the field, coming out, emerging from the center. And then we know that the field forms loops, and so you just trace the loops back through the loop. You trace the field lines, back through the loop. So that's the way of getting this is the magnetic field of a single current loop or a single magnetic dipole. So here's just again, the author sometimes likes to complicate you by giving you different ways in which you can get the direction. For me, this way too, which we've discussed, is easier. So you really don't need to memorize all these different ways. Just pick which way you like and use it. So here's an example. If you have a current going in the counter, here it's going in this direction. So it's going up, then it's coming here and coming back down. And so if you take your hand and you curl it in the direction of the current, you would see that your thumb would point to the right, and so the field lines are coming out of the center to the right. And so then this is the north pole of the magnet, of the loop is to the right, and the south pole is to the left. And if you stick that next to a bar magnet, the north pole is facing the north pole of the bar magnet, they're going to repel one another. And so if you take the same current and run it through here, and you put the south pole of a bar magnet here, they would attract, right? Because the north pole of the electromagnet, the current loop, is attracted to the south pole of the bar magnet. So this current loop does behave just like a bar magnet. Same magnetic field, and it has a north pole, and it has a south pole. Okay, so we're going to do an example here. So you have a loop, and we're given that the magnetic field, and so the field lines are emerging from the center of the loop pointing downward, and they're re-entering the loop coming back around here from this direction. And so the question is, what is the current direction of the loop, and which side of the loop is the north pole? Okay, not the one where Santa is, but the north pole of the magnet. So the easy one, let's do the easy one. The north pole of the magnet is the side in which the field lines are emerging from the center. Okay, well, they're emerging from the center here on this side of the loop, below the loop, and so this bottom side of the loop is the north pole of the magnet, and the top side of the loop is the south pole. So now that we have that, what's the direction of the current? Well, you have two choices, right? It can either be going counterclockwise or it can be going clockwise. So let's try our thumb here. So if it were going in this direction, meaning counterclockwise, that would imply that you would curl your fingers counterclockwise, your thumb would be pointing up, which in that case the field lines would be emerging upward from the loop center going up. Well, they're not doing that, right? They're going down. So the current must be going clockwise. And we can see that if you take your hand and you curl it in the direction of the current, which is clockwise, your thumb is pointing down, and so the field lines are emerging from the bottom side of the loop. Okay. So I think we've done several examples by this. So you should be able to relate the current direction, clockwise or counterclockwise, for a loop to the direction of the magnetic field. In other words, which side is the North Pole where the lines are coming out of the center, which side is the South Pole where they're coming back into the center. Okay. So let's do an example here of practical importance. So given that the human heart produces a very weak magnetic field, and the field produced by the heart is a dipole field. It produced the same field as a current loop in the outer layers of the heart. So you have circulating charge around the outer layers of the heart, and so circulating charge ions create a current loop, right? And so we can model this magnetic field produced by this, quote, current loop. We can model that as the field of an electric dipole, which is a current loop. Okay, so if we're given that the magnetic field strength at the center of your heart is 90 picotesla, where 1 pico is 10 to the negative 12, very small, and we know that the human heart is about an 8 centimeter diameter, or close. You can think of the current as going around the loop, around the outer layers of the heart. So you have these ions going around a loop of 8 centimeters. Well, that's a current loop, right? So the question is, what current must circulate around the heart to produce this known magnetic field of 90 picoteslas? Okay? And then given that current, what is the heart's magnetic dipole moment? Okay? So we can use the magnetic field at the center of the loop. Remember, so the center of the human heart is at the center of the loop. And so we can use the equation for the magnetic field at the loop center. And we know B, we know the magnetic field strength, we know the radius of the heart, but we're trying to find the current. So we can solve this for current, and you can plug in 90 times 10 to the negative 12 Tesla. You can plug in the radius of the heart, which is 4 centimeters or 0.04 meters. You plug in mu naught, and you get that the current is very, very small, okay? So there's a very, very small current, 5.7 times 10 to the negative 6 amps, or 5.7 microamps surrounding the heart. So there's a very small current surrounding the outer portion of your heart, which creates a very weak magnetic field. Okay, but nevertheless, it is used to diagnose heart problems. Don't ask me about the details, but it is. So once we know the current, and once we know the area of the heart, if the loop is pi r square, if it's a circle, we can multiply the two together, and we get that the dipole moment is 2.9 times 10 to the negative 8 amps times meter square, right? And so that's the units of dipole moment. It's area times current. Area has units of meter square. Current has units of amps. Okay. So you should be able to apply this equation here to get the equations for the magnetic field on the axis of the dipole, and then set z equals 0 to get the equation at the center, and then have z square much, much bigger than r squared to get the dipole far away from the loop. So you should be able to solve in these three cases. You should be able to apply the equation. You should be able to sketch the field lines for the dipole, for the loop, and you should be able to relate the direction of the field lines, which pole is the north, which pole is the south, to the direction of the current using your right hand. So that's what you should be able to do as far as a current loop. Now, if you add many loops together and we wind them around a core, and you wind them really tight so that there's no air gap in between, we get this device that we call a solenoid. Okay, and so if you have many different coils, many different loops, a solenoid's purpose, as we'll see in a minute, is to generate a very large magnetic field inside of the coil. A very large uniform magnetic field. Okay? And we saw something similar with parallel plate capacitors, right? If you charge up a capacitor to put equal and opposite charge on two different metal plates, that the electric field in between the plates is very large and uniform. So the parallel plate capacitor creates a uniform electric field. A solenoid creates a uniform magnetic field. And so this is used in any instance where we need a very uniform field, meaning the magnitude and the direction are constant, and they are inside of this coil. So there's several applications with these coils, including MRIs, motors, and any application where we need a large or a uniform magnetic field. The solenoid is used to generate such a field. So what we want to do now is we want to get an equation for the solenoid. But first we need to understand what's going on here physically. Okay, so to do that we go back to our magnetic field for a single loop. Okay, and again, at the risk of beating this to death, the current at the top is coming out of the screen toward you, it's going around the loop, and it's coming back into the screen at the bottom. And that means that if you curl your hands in the direction of the current, your thumb will point to the right, which means the field lines are coming out of the loop to the right, and then they're going back in. They're re-emerging from the left. So your north pole is to the right, and your south pole is to the left. Okay. Now suppose that we add some more loops here, and we'll just start off with 3 for visualization. Okay. And we're going to apply superposition, right? So the field at any point, due to all 3 loops, is just the sum of the fields created by each loop. Okay? So if we put 3 loops here, we know that the current is going in the same direction through each loop. And so all of the fields due to each one will point to the right inside the loop. And so if you add 3 vectors all pointing to the right, you're going to get a big vector pointing to the right. And so you can get a large magnetic field along the axis of the solenoid inside the loop, inside the coils. Okay? Now what about outside? Okay, this is a little bit tougher here. So let's look at this one point here. So here's the field line due to loop 1. Okay, that's coming in this direction, so we can draw that as B1. And here's the loop due to here's the field due to loop 3, right? And that one is coming back, and it's going to go back through the loop again. So it's in this direction. And then loop 2, we're right above the loop. And so that field line, if you go look right above the loop, that's pointing to the right. And when we add all 3 of these vectors, they very nearly cancel one another. Okay? So in other words, the field lines cancel one another outside the loop, or the coil, and they reinforce one another inside. And so the net result is a strong field inside the loop, inside the coil, and a weak field outside the loop. Okay, but not quite 0 yet. Now if we keep adding more, so we only had like 3 turns here, 3 coils, or 3 loops, I'm sorry. If you had many of them and you made the spacing approach 0, so in other words, we wound our coil tighter here, go back, so there's like very little gap, and we have many turns, then you're going to have many of these loops reinforcing inside and helping to cancel outside. And so the net result when we wind many turns of wire or loops is that you get a very strong field inside the coil, and you get a field that's very close to 0 outside the coil. Now you can look in the text, your author uses a trick called Ampere's law that we really don't have the time to develop the mathematical formalism. But you can do the mathematical integration, he does it in the book, and you can show that the magnetic field due to the solenoid inside the loop is mu naught, the constant, permeability of free space, times the current, times the number of turns, the number of loops, divided by the length L of the coil. Okay, and he calls little n the number of turns per length. It's basically a measure of how densely packed the turns are, how tightly wound they are. And so you can get another form of the magnetic field equation. It's sufficient in this right now just to keep it as mu naught I times the number of turns divided by the length. And that field is along the z direction. And so for this example here, the current is coming toward you at the top and back into the screen at the bottom, and that gives rise to the magnetic field pointing to the right. So what you can do is you can wind this coil up, you can make many turns, and you can wind it on a McDonald's straw. You just need some core or something to wind it around, and you wrap up many turns of wire, and we'll see in a minute how to create a solenoid. And here's the iron filings. They give the direction of the field. The field lines are emerging from the inside, and they're forming loops on the outside. So you get a very strong field inside. A real solenoid looks much different because you don't have all these big air gaps in between. So it's a lot stronger inside, a real one, and it's much weaker on the outside. So you can wind this on a McDonald's straw or any air core. If you really want to get a strong field, we're not going to discuss it in class, you can wrap it on some iron cylinder, a little chunk of iron material, and you wind it on that, and you can get a much, much stronger magnet. And so most practical magnets are like a transformer, for example, the ones that change the voltage and the current for the power on your power lines. Those typically have these iron cores with several coils of wire wound around them. So we'll stop here and do a little video. So that's how you create a solenoid. She just wound it around a piece of a syringe. You can wind it around a McDonald's straw or anything, but if you really want to get a strong magnetic field, take a little chunk of iron and wind it around the iron, and you'll be able to pick up much more than just that wimpy little screw that she was able to pick up. You can create a very, very strong electromagnet, okay? And so the field of a solenoid is very, very strong inside here, and it's very, very weak on the outside. It's uniform. If you look at the field lines, they're uniformly spaced. If you look at the blue in here, they're uniformly spaced inside the solenoid. Same direction, same magnitude. They're all pointing to the right. And you can get that from the current direction. If you know the direction of the current, you curl your thumb. So the north pole of the magnet, the solenoid, is here, and the south pole here. And this produces the same field as a bar magnet. So a solenoid functions as electromagnet, right? If you make the current strong enough and you wind many, many turns of wire, you can pick up things just like a bar magnet can. Okay, so you just create an electromagnet. So let's do an example here which illustrates some practical concerns. So here's magnetic resonance imaging. Okay. And you need a very strong magnetic field inside the MRI machine, a very strong uniform field pointing along the axis, and the patient is being pushed in along the axis. So you have this coil, and there's a coil all the way around the inside of this MRI machine. There's a coil with many, many, many turns of wire around the perimeter here. And suppose that you need a magnetic field strength inside the MRI of 1.5 Teslas. That's a pretty strong field. And suppose that the solenoid surrounding the patient, this area in here, is 1.8 meters long. And suppose the diameter is 75 centimeters, which is about 30 inches. Okay, so we know the diameter, and we know the length, and we know the magnetic field, and we also know that you have a single layer of wire, superconducting wire, we'll get into why in a minute, and the wire has a diameter of 2 millimeters. Okay, so the question is, what size current do you need to run through these wires to produce the necessary 1.5 Tesla magnetic field inside the MRI machine? Okay, so we're like, okay, well, we're trying to relate current to magnetic field, and we're talking about a solenoid or a coil, so we must use the solenoid equation, right? The magnetic field inside B, the magnitude, is mu naught I times the number of turns per length. And in this problem, we're solving for I. Okay, so let's look. Do we have everything we need? We need magnetic field strength. Yes, 1.5 Tesla. We need the length of the coil. Well, yes, we have that. That's 1.8 meters. Mu naught is a constant. We're not given the number of turns of coil wire. So can we solve this? Well, we're given some other things. Let's see what we can make out of it here. So can we get the number of turns? Well, we know that the coil is 1.8 meters long. We know that the wire diameter is 2 millimeters. Okay. And we know that the wire is wound in a single layer. Okay, well, that might help us here, right? If we know the length and we know the diameter of the wire and we know that it's a single layer, we know that the length of each turn is 2 pi r, right? Where r is the radius, okay? So how many turns can we fit in 1.8 meters of a single layer if the wire diameter is 2 millimeters, okay? Well, we know that if these turns are stacked together here, here's the diameter of the wire is 1 turn. So for this example here, we could get 1 turn, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And so the length must be equal to 18 times, in this case, the diameter of the wire. Okay? So we can use the same in this case. So we know that the total length is 1800 millimeters or 1.8 millimeters. We know the wire diameter is 2 millimeters, so that means each turn must be 2 millimeters of length. Well, 1800 divided by 2 means the number of turns must be 900 turns from one end to the other. Okay, and then we can plug in 900 for turns, and we get that the current is 2400 amps. Okay, so that's 2400 amps of current going through these wires. And that's a pretty big current, right? So that tells us that's a lot of current, and what's a little bit hidden here in this formula is that you need a big current, right, to get a big magnetic field. And you also need a lot of turns. So you need a big current and a lot of turns, right, to get a big field. Okay, so the problem is if you need a lot of turns, you need a large wire. You need a long wire, right? Because you have to make more turns, you need a longer length of wire. Well, if you have a longer length of wire, the resistance of most wire, remember it increases with length, the resistance, which means your current decreases, right? So your current, longer wire means it's harder to push current through it. So there's these are like competing influences in practice. The other issue is because there's more resistance in a longer wire, this coil is going to heat up more. It's going to generate a lot of heat, and it can get pretty hot. Okay, so that's the problem in practice, is you try to wind all these coils of wire, but in doing so, you're going to generate a lot of heat, and your coil is going to get hot. Now, superconducting wire, such as that used in MRIs, is different because superconducting materials have these materials that have no resistance to current. And so then we don't heat up the wires, and so that's why in these MRIs you can't just use regular wire, you have to use these superconducting materials. So that's pretty much it for right now for this section. What you should be able to do on an exam is you should be able to apply the equations for the magnetic field due to a single loop and a coil and a solenoid. And you should be able to relate the field to things like the current and the number of turns, etc. And finally, then you should be able to sketch the magnetic field for each case. So I know we've covered quite a bit here. I'm as tired as you are. So we'll start off tomorrow with a little bit of a review, and then we'll go on to magnetic forces on charged particles.